Okay, so what we want to do is we want to turn this to a histogram. And a histogram is a particular way of viewing data. And it views it in a way that it fills the space for us. So I'm going to use the same data set. And what we're going to do is we're going to have a vertical axis that has a place for our counts, and then we're going to have a horizontal axis that has our data values. So here we keep our data values. Hand on this correctly. Data values. Actually, I'm going to move this down a bit so I have room to write some other stuff. So here goes our data values. Along the x-axis, we'll put our data values. All right, and on the horizontal axis, for right now, we're going to count. And so if we look, we had 7 bins. So I'm going to try to make 7 even bins here. There's 2, 3, 4, 5, 6, 7. And I'm going to label them by their midpoints. So if I go back to my data set, which I have up above there, but again, if you're following along in the slides, the midpoint for the first bin was 172.5. The midpoint for the second bin, or the second class, was 208.5. I want to stagger these so I can kind of... This midpoint was 244.5. And this midpoint was 280.5. This midpoint was 316.5. And this was 352.5. And the last midpoint was 388.5. Now again, this represents my lowest value, which was 155, and my upper class value here was 406. And so we kind of have the space put out for all of our data. And then we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is counting, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9. And so we're counting how many pieces of data. And so if we're thinking we're moving our data in and they fall into the bins, kind of like the Plinko or the Chinese marble games, where you drop a ball and it would fall over the nails and it would eventually land in the bottom, and whichever one it landed in you kept, or you got the score that was printed on the card. Well, here each piece of data we pull from our data set, and we had 1 thing in the first bin and 2 things, and all said and done, when we counted them all up with our tally marks, we had 3 things in the first bin. So I'll color this in. Let me get a slightly bigger brush here, I think. Yeah, we'll just color it in so it's visually showing us that in this bin, we have 3 pieces of data. It fills up to the 3rd level here. And then when we do our next bin, we only had 2 pieces of data. So we'll go across from 2 and over. Right, if we look down our, whoops, yep, 2 pieces of data. We're looking at our frequencies. And so we're making a graph that relates to each frequency. Now, in our third bin, 244, that had 5 pieces of data. I'm going to pull my pen back up here. So I want to make the bin like this. 5 pieces of data. And then in our next bin, had 6 pieces of data. So up here, 6 and over. And then this bin had 7 pieces of data. And then in 352.5 had 4 pieces of data, so it comes up this high. And the last bin had 3 pieces of data, so it's as tall as the first one. And we fill all these in, and this gives us a shape. And the shape we're going to find is statistically important. Histograms shape tell us how the data works. Notice we have this area in here, this taller part, where most of our data is. I'm just scribbling this in because visually we kind of color them all in. Now I hike, and so to me this is like a mountain. And the peak, most of my climb is in here, and the peak, or where the most of the data in one spot, is here. And we come back down. Now my eye is drawn to this little extra step up here. But we have a shape. And a lot of what we're going to do numerically is try to find a way to talk about these shapes numerically. And much of the section 3 of this chapter looks for ways of describing the numerics of these. Now, in histograms, we need to refer or we need to make sure that our class boundaries have no gaps, and so the sides touch. And so to make sure the sides touch, when we make these things, we come back up here and we have to look at these numbers. 155 to 190, and then 191 to 226. I'm just going to look at this class, but there's a gap. And to make these touch, this gap has to be closed. Well, the gap between 190 and 191 is 1. So if I want to be fair, I can put half of it here, and the other half I can put here. And I do that by turning this to 190.5 also. And if I want to keep everything the same size, I make this 154.5. And so what I do is I take that gap of 1 and I add it to each class, but I do it so that they each get parts of it. What ends up happening is my classes become, this becomes 154.5, this becomes 190.5, this becomes 226.5, this becomes 262.5, 298.5, 334.5, and 370.5. Well, the upper class limits get that extra half. And so I could just put a 0.5 on all of these. Right? And this makes our bins touch. And what that's going to help us do is it's going to make this shape that we've created, so this becomes 406.5 on the upper end, this shape fill in, and it always overlaps, and the shape becomes descriptive of any size thing when we try to extrapolate this to other data. Now, the thing that helps us extrapolate it to other data, and the thing that could emphasize how important the shape is, well, I want to make a histogram out of the relative frequency. And so if I make a histogram out of the relative frequency, I have to put in here, this has 0.1 of the data. This has 0.07 of the data. And I have to turn these bars into percentages. Now the book goes through saying, hey, do this, this, and this on this. I want to show you the easy trick and something that actually really importantly highlights the meaning of the shape and why I'm saying the shape is important. If I come through and erase my axis here, and I re-put on my axis the percentages. So this is 0.07, this is 0.1, this was, I think, 0.13, this was 0.2, this was 0.24, was it? I have to look back on my sheet. I'm a page away from it. 0.23, my bad. Sorry. 1, 2, 3. And so by changing the scale so that it talks about relative frequency, it hasn't changed the shape. And this is going to be the key to inferential statistics when we look at histograms and probability distribution functions. When I'm talking about actual counts, that shape can also talk about percentages. And the shape can help us translate between the two. And so when we look at relative frequencies, this could go for n equals 1 million, right? If this is representative of 1 million, these relative frequencies come through, multiply through, tell me how many things out of a million are in here. But it doesn't change the shape of the distribution of the data. And so it's an important thing to note that the counts or relative frequencies will give us the same shape. And that kind of hints at something that's underlying all the statistics there. And for that to work, we need to make sure our bins go together, and we need to get that extra 0.5 on our endpoints here. And so this is 154.5, where we start from. All right, now there's another thing. I'm just going to change color here that sometimes people do, and it's to make our data pop on a particular thing. And the particular thing we want to see is how fast the data is changing. So if I plot a point at the midpoint and each value so the midpoint and the value of the counts or the relative frequency, and I connect those by lines, this raggedy graph, not the histogram underneath, but this raggedy red graph that we draw, is called a frequency polygon. And a frequency polygon starts from 0 and it rises to the midpoint and it follows the midpoints around. And what this is doing is it's letting what a line means help us, because each of these are little lines, and lines have this formula, mx plus b, wherever I've started, and the slope is the rate of change. And that's a mathematical thing that we can look at. But by plotting it as such, what we can say is, hey, I start off at 0, and really quickly, because my line is steep, I rise up. Now this line falls down slowly. This line rises up, just as steep as this one. This one rises up not as steep. And the visual description of the line gives us wordage around around the rate of change. And so we're using the graphical element to explain to our viewers, or for us to read, something mathematical that is happening. Now we will learn how to pull numbers out for the different mathematical things, but by graphing it, we can use the language that comes from the geometry to describe what's happening. And so frequency polygons describe how quickly the data is changing. All right, and that's covered the histogram, the frequency polygon, and the relative frequency distribution. There's one other thing we make, and I'm going to put it here, and it's called an ogive. Now, ogives I have a particular bias against. They tend to pop up in standardized tests, and they're a way of talking about the cumulative, whoops, that's the wrong tool. They talk about the cumulative effects of things, and they take cumulative data for us. So ogives plot the cumulative data. And so again, we're going to look at the midpoints. So I'm just going to list the midpoints of my graph, or actually the endpoints. We want the endpoints because we want to know how much we have by the time we get to the end of a class. So when we construct an ogive, we look at the end of each class and we figure out how much has made it to the end. And so in our case here, let me replot the endpoints here. are the upper class boundaries. Now we do this using the upper class boundaries that came from our histogram with the extra 0.5 because we can't have any gaps in our data. So I'll write each of the new upper class boundaries. $298.5. Okay. And this is a 370.5 and 406.5. Now we will start, and we will need to make a scale going up here. I think I might be able to fit it. Yeah, we'll fit it there, barely. I'm a little tight on the upper end of my graph, but these are ogives. And so our data starts at 0. And the cumulative frequency, again, you have the chart on your slide there. Our cumulative frequency at 190 was, or in the first class, was 3. So we'll put a point there. And then in the second class, our cumulative frequency was 5. So let's see, 3, 4, 5. And then in our third class, our cumulative frequency was 10. So that's 5, 6, 7, 8, 9, 10. There's 10. So we're up to here. And then in our cumulative frequency in the next one was 16. So 10, 11, 12, 13, 14, 15, 16. So we're up to here. And then 23. Then 27. So 27 is here. And then we end at 30 because 30 is our data sets. And we connect these with lines. And what an ogive shows is how you're accumulating your total data and how quickly your total is growing, the total pieces of data. And again, this tends to get shown where I've seen ogives a lot are standardized achievement tests where they talk about how many are in the percentile you are, how quickly you're going towards the upper end of the scores. Or I've also seen it in like saturation rates in a liquid or whatnot. I visually recognize that here when you're steeper, you're growing more data, and it's showing that a lot more data is being added in this steep part, and the total data is growing slowly here. And this again highlights that midsection in the histogram. If I come back up here, this midsection where most of the growth was. And so ogives can show you how quickly you're growing by how steep the curves are. I find them visually a little hard to process, and I don't see them get used as much as other forms of graphing, so I will focus on histograms a lot. You will find the histogram translates to the probability distribution functions that we use a lot going forward, and so a lot of effort will go into the histogram for us. All right, and so that are the main graphs from this section. I'm going to do some things in section 2 on stem and leaf plots and dot plots, and then pie charts and other graph forms.